Welcome to this explainer. Today, we're doing something really cool. We are popping the hood and deconstructing the literal nuts and bolts, well, actually the glass fibers and polymers, of a high-performance surveillance UAV. You know, we constantly see these sleek machines cutting through the sky, but right now, we're going to break down exactly how they're built, layer by layer, starting from the physical shape of the wing, all the way down to the microscopic fibers holding the whole thing together. Let's get into it. Okay. Let's dive into the fundamental puzzle that aerospace engineers face every single day. How on earth do you create an aircraft that is robust enough to handle the absolute extreme stresses of flight, yet light enough to actually be efficient? Whether you're designing for a military surveillance op or a civilian search and rescue mission, balancing these two extremes is everything. I mean, in aviation, every single gram matters. Literally. If your drone is too heavy, the battery drains in minutes and it can't carry its payload. But if it's too flimsy, the aerodynamic forces from just a simple sharp turn could rip its wings right off. To see how engineers actually solve this massive puzzle, we're going to visually build this drone together. Our agenda covers 4 key steps. First, anatomy of a delta wing. Second, the magic of glass fiber. Third, powering the flight. And finally, testing the virtual skies. All right, starting with section 1, anatomy of a delta wing, the blueprint. Now, what's really fascinating to see here is that the delta concept isn't just one single uniform shape. From tailed and tailless configurations to cropped, lambda, and diamond wings, this huge geometric variety allows engineers to dial in specific aerodynamic benefits. The big core advantage of the delta shape is that it can offer way higher power efficiency than your traditional straight wing. They are absolutely brilliant at utilizing something called a leading edge vortex to generate a ton of additional lift, especially when the drone is pitched up at higher angles of attack. So, the crucial concept to grasp here is aspect ratio. Put simply, it's comparing the wing's span, how wide it is, to its mean chord length, which is how deep it is. Delta wings deliberately use a really low aspect ratio, the relatively short and wide completely opposite to the long, thin wings you'd see on a commercial airliner. And this is a very intentional design choice. This specific low aspect ratio massively improves the aircraft's roll reaction and overall maneuverability, which is exactly what lets a surveillance UAV make those tight, incredibly responsive turns in the air. Moving right along to section 2, the magic of glass fiber. This is essentially the skin and bones of our drone. Check out this microscopic view. To keep weight down, we are completely ditching traditional heavy metals and building the physical structure out of composites. Think of that yellow polymer matrix you see like an incredibly tough, highly specialized glue. It encases and holds together thousands of tiny, microscopic bundles of glass fibers packed tightly together. The matrix protects the fibers from the elements and transfers aerodynamic loads perfectly across them, while those glass fibers act as the core reinforcement, giving the drone massive tensile strength. But, you know, engineering is literally always a game of trade-offs. On the plus side, glass fiber, or FRP, gives us this amazing strength-to-weight ratio, which is exactly what we need for maximum flight efficiency. It's also naturally corrosion resistant, so unlike metal, it's not going to rust away if you're flying in high humidity. However, we do have to carefully design around its flaws. Compared to something like carbon fiber, glass composites can get a bit brittle under high-stress situations. On top of that, over time, the matrix can actually absorb moisture from the air, which can slowly degrade its structural integrity if it isn't properly protected during manufacturing. Looking at the raw data for e-glass fiber, the numbers really speak for themselves. It boasts an elastic modulus of 73.5 gigapascals, which means it is unbelievably stiff. But the real game changer here is the density, just 2.57 grams per cubic centimeter. These precise numbers prove exactly why it is the ultimate lightweight substitute for traditional clunky aluminum when you need to build a flying wing that minimizes weight, but doesn't sacrifice the rigidity you need to survive flight. Okay, section 3, powering the flight. Time to add the muscle. With our lightweight, highly durable composite frame theoretically built, it's time to install the hardware that will actually get this 2-kilogram payload off the ground. For propulsion, this specific UAV relies on the Raystar 2216 brushless motor. Now, while servo motors are awesome for tiny precision movements like steering, brushless DC motors like this one are the absolute gold standard for producing forward thrust. They offer fantastic positional stability and hit that perfect sweet spot of efficiency and power consumption that you absolutely need for medium-sized surveillance missions. Notice the 1400 kV in the motor's name? To understand how engineers actually pick a motor, think of the kV rating kinda like the gearing on a mountain bike. Our 1400 kV rating means the motor will spin exactly 1400 times a minute for every single volt of electricity you push into it. A higher kV rating spins faster but sacrifices torque, while a lower kV spins slower but gives you way more pushing power. For a medium-sized delta wing, 1400 kV is the absolute sweet spot. Supplying the voltage to make that happen is a 2200 milliamp hour lithium polymer or LiPo battery. LiPo batteries are chosen because they use a unique polymer electrolyte, unlike the liquid electrolyte you'd find in an older lithium-ion battery. This is a big deal. It means they can store an immense amount of power while staying drastically lighter, and they can be molded into versatile, space-saving shapes to perfectly fit inside the drone's fuselage. Finally, to convert all that electrical and rotational energy into actual physical thrust, we attach 9-inch propellers. In aviation, you absolutely cannot just slap any random propeller on your aircraft. They have to be meticulously matched to our motor's exact RPM specs, the battery's voltage, and the total weight of the drone. If you miscalculate this even a little bit, you run the risk of overheating and completely burning out your incredibly expensive electronic speed controllers or even the motor itself. It's all about matching components to get maximum thrust safely. Which brings us to our final section, number 4, testing the virtual skies in our virtual wind tunnel. Because obviously, once our drone is theoretically designed and assembled, we don't just chuck it off a cliff, cross our fingers, and hope it flies. Instead, engineers use highly advanced open-source computational fluid dynamics software, specifically a program called XFL5. This simulates exactly how air molecules will interact with our specific wing geometry. It calculates the exact coefficients of lift and drag, letting us fully optimize the design digitally and spot any fatal aerodynamic flaws long before a single piece of glass fiber is ever cut. But real quick, before we look at the results of those digital tests, you need to understand what a drag polar curve is. Think of it as a literal scorecard for the wing's performance. It visually plots how much aerodynamic drag we are suffering on the horizontal axis against how much lift we are successfully generating on the vertical axis as the drone pitches up and down during flight. All right, here we go. This brilliantly illustrates our virtual wind tunnel output, comparing the performance of two different wing cross-sections, the MH45 and the MH60. Looking at these curves, see that shallow area? That's the low lift region, which represents normal level cruising flight. As the curve turns steeper, you're in the high lift region, used for takeoff and sharp maneuvering. But if the drone angles up way too steeply, you hit what's called drag divergence. See that sharp hook? That's where the smooth flow of air separates from the wing. Lift completely dies, drag violently spikes, and your aerodynamic efficiency just falls off a cliff. Ultimately, the specific MH60 airfoil shape was selected for this drone. Take a really close look at that beautiful reflex curve at the back of the wing. That shape provides a highly stable, zero-moment flight path, which is absolutely crucial for real-world missions like smooth aerial topography or precise agricultural surveys. It naturally resists wobbling up and down in the air. But guys, what's truly mind-blowing to me is that this incredibly specific shape wasn't just invented from scratch by an algorithm in a computer lab. It was actually copied directly from nature. Yeah, you heard that right. Engineers achieved these incredibly low-drag, high-efficiency flight characteristics by observing and literally mimicking the wing shape of the prehistoric Quetzalcoatlus. This was a toothless pterosaur, and it just so happens to be the largest flying animal to ever exist on Earth, with a massive 35-foot wingspan. Millions and millions of years ago, this giant reptile achieved fully gliding, highly efficient powered flight using this exact same aerodynamic profile. How wild is that? So, as we wrap up this explainer, I want to leave you with this thought. We've walked through complex aspect ratios, microscopic glass fiber matrices, and digital fluid dynamics. Yet sometimes, the absolute most advanced, highly efficient technological blueprints of the future have actually already been field tested by millions of years of natural evolution. It really makes you wonder, as we continue to push the absolute boundaries of aerospace engineering, what other ancient, perfect designs are just waiting in the fossil record to be rediscovered? Thanks so much for exploring the amazing mechanics of the Delta